my pleasure to introduce Professor Yu-Jung Chen from Central University. He's currently the chair of the physics department at Central University. He's also the head of secretarial division of the Physics Society. I don't really know how you survive, but and he's also the chair of the interdisciplinary study at NCU for a bachelor's degree. In addition, he has been working extensively on experiment on astrophysical eyes, and he has a lab working on photoprocessing and spectroscopy, and he's currently a distinguished professor at NCU, and he also got his degree from NCU.
Yeah.
And he went to South California for postdoc.
Yeah.
And he has many different interesting adventures. And if anyone is interested, ask him. Okay, let's welcome Yu.
Okay, thank you. Thank you for introduction, and I'm so happy can give a talk here. Actually, this is the first time, and I come here and to give a talk. Yeah, the first time, yes. So, and today I will talk about the astrophysical ICs in the laboratory. Actually, in my talk, I prepared the two parts. The first part is with the energetic source irradiation, and another one is without the energetic source irradiation. But actually, last night when I prepare and restructured the whole slides, and I found that maybe I put too many slides. So I'm not so sure if today I can just finish the two talks. And actually, I think the second talk is you will be more interested in the second talk because it talks about the interstellar dust and the dust effect on the ice structure and also the infrared absorption spectrum. But because the first topic and I spent more than 10 years, so it's my first priority I want to introduce to you. Okay, so as all of you know that in the interstellar medium, 99% is gas and only 1% is dust. And due to the environment, the temperature is very cold. So the molecules will condense on the surface of the dust and to form what we call the interstellar ice. And in space environment, there are so many the energy sources. So for example, like the photons and also cosmic rays. And no matter if the photons or cosmic rays, they will just deposit energy to the ices. And cause the ices, the molecule dissociate. So when it's just dissociate, and although the temperature is very, very cold, like the 10 Kelvin, but they still have the mobility, can just migrate a little bit and to react with the neighbors and to form the more complex the molecules. And this process we call is the irradiation-induced chemical reaction. Besides the chemical reaction, and when the energy deposits to the ice, and they can cause lose the ice, the molecules, or the radical, or the atoms, desorbing from the surface. So this process we call irradiation-induced desorption. Okay, so what is the laboratory astrophysics and also astrochemistry? Okay, so in laboratory, if we want to achieve like the environment of the space, so we need to provide the ultra low pressure and the ultra cold environment. So in laboratory, we use an ultra high vacuum chamber and with the pumping system, and to reach like the pressure is the 10 to the minus 10 to. Actually, for example, the 10 to minus 10 to, roughly the particle number is like the 10 to the 7 or 10 to the 8 molecules per centimeter cubic. So actually, this compared to the dense cloud is much, much higher. So if we transfer the pressure in the dense cloud, it should be like a 10 to the minus 14 torr. So, but in the ultra high vacuum, the research to reach the 10 to the minus 10 torr or 10 to the minus 11 torr, actually it's quite difficult. Even at the National Synchrotron Radiation Center, the storage reading and the pressure is only the 10 to the minus 11 or 10 to the minus 12. So, but even though the pressure is not really the match like the pressure in the dense cloud, but for us, this is clean enough. And the temperature, we can control from the room temperature to the lowest temperature is the 12 Kelvin. And it's a cross state. Actually, it's just like an air condition. It's a compressor, but inside the compressor is the helium. So the compressor will compress the helium and to very high pressure, and to the cross state. This cross state is just like the second stage. And this the two stage will still compress the helium to the more higher the pressure. So when it's expansion and it will lose the energy, so it's become very cold. So it can take out the heat. Okay, so by this way, usually from the room temperature and to reach like the 12 Kelvin, we need to spend like 3 hours. So in my lab, so each student, if they want to do experiment every day, they need to spend like 1 hour before prepare the experiment, and 3 hours for the cooling down, and another 1 hour for the deposition, the ice, and spend like 4 hours, and for like the irradiation, and spend another 3 hours, and for the warm up. So the total is almost the 12 hours. So if students come to the lab during the noon, that means that they will go home or go back to their dormitory after the 1 o'clock in the morning. Okay. So, and this is a cartoon to show, this is we call cold finger. So it's connected to the cross state. So this is the whole cold finger will reach like 10 Kelvin. And usually in this part, and it's the substrate, and we use the calcified window, zinc window, or the potassium bromide, because it's the infrared transparent. So we need to use this kind of the material. Actually, the cost, the best is the cheapest is the potassium bromide. But in Taiwan, you know the temperature is changed hugely, and also the weather is quite humid. So if with the potassium bromide, usually if you did not take it very care and it will melting, just that you put on the table few days, it start to melt. So here, and we use the calcified window because it's more expensive, but you can use the methanol to clean the window. But with the potassium bromide, you cannot use any of the liquid to clean it. When you clean it, it starts to melting. Okay, so we eject the molecules and into the ultra high vacuum system, and because the cross state make the cold finger is very cold. So when the molecules stick on the substrate, it will just condense on the substrate and to form what we call the interstellar ice. Okay, so during the deposition, we can use the laser to do the interference, the monitor. So you can see like this, the different cycle, and we can notice the ice thickness. But for example, sometimes we need to, because we want to make more the compressed organic molecules, so we will deposit very, very thick ice. So by the naked eye, you can see this like the interface ring and from the window very clearly. Okay. So this is a top view of our system. So usually we use the infrared to monitor the ice in solid phase, and use the quadrupole mass spectrometer to monitor the ice when the molecule dissolving out of the surface. And here is use the energy source to do the irradiation. Here I show you like it's the normal the infrared spectrum when we start to before we deposit the ice. But because in our atmosphere, there are so many water and the CO2. So you can see in the gas phase, this is the G, it means the gas phase. And we want to improve the signal to the noise ratio. Otherwise, when we produce some product, and there the absorption feature located in the few regions, is very difficult to observe it. So, and we put the infrared into the vacuum chamber. So that means the infrared just goes through the vacuum chamber, so we can remove all of interference from the atmosphere. So you can see this the red line. We remove the water and also remove the CO2. So it can make our the sensitivity much, much higher. Okay, so no matter from the diffuse cloud, the dense cloud, or to the protoplanetary disk, and to stellar system, and to the mass loss, no matter in which the stage, and we more interested in the dense cloud, and also the protoplanetary disk, because in these two regions, and the interstellar ice can form, is more abundant, and also can produce more the compressed organic molecules. And in our laboratory, we can use the energetic sources. The first one is a UV lamp. Actually, this is the hydrogen, discharged hydrogen, and to make it like the plasma, and it will emit the UV field. And another one is electron gun, and we bought it from the Kimball physics, and this electron gun can provide the electron with the energy from the 100 and to the 5,000 electron volt. And then we just bought the hydrogen atom beam, and it was delivered to Taiwan today. And with this one, we can do the hydrogenation to mimic it in the dense cloud because there are a lot of hydrogen. So hydrogen will just impinging with interstellar ice and will cause the hydrogenation. And if we need to use the X-ray, and for example, in the protoplanetary disk, when the protostar formed, it's emitted very high intensity the X-ray. So we went to the synchrotron radiation center, and with the specific beam light, it can provide the photon energy from the 80 and to the 1,250 electron volt. And in the first talk and in the end, I will also introduce this VOV beam light and why we need to use it, because generally in the laboratory, this kind of UV field, it cannot select the photon energy. Because if you select the photon energy, the photon flux is too low. So if it's too low, maybe you need to irradiate like more than 1 mass, otherwise you can see nothing. So the synchrotron provided this the monochromated photon light source, and with very, very high the photon flux. Okay, so the first topic is according to the accretion module in the coded molecular cloud, on the molecule beside the hydrogen molecule, they will just expect to stick onto the ground surface, and within like less than 1 million years. Okay.
1 billion.
1 million.
10 to 9.
But this is 10 to 9 divided by the number density of the hydrogen. So usually hydrogen is like 10 to the 4 or 10 to the 5. So it's 1 million, less than 1 million. It will all condense and to be the solid phase. Okay. So, but there are so many observational data shows that they still can see in the dense cloud, its age is more than 1 million. It's like 10 million, but it still can observe like the CO and it's the rotational transition. So that means the CO still in the gas phase. So according to the accretion model, it's impossible still in the gas phase. So what happened? So scientists proposed the few possible mechanism. The first one is a VUV-induced desorption, just like what I said. The VUV photon deposit energy to the ice and cause the ice molecule just escape from the surface. And also the cosmic ray, the whole grand heating and the spark heating is depend on the interstellar ice is the size. So when the size is very large, the large is like the micrometer, so it's a spot heating. And when the size is like the sub-nanometer, and it's like the grand heating. And also when lose the molecules inside the ice, they have the chemical reaction, they will release the heat, and they will cause like a weakly bonding molecular dissolution. However, according to the theoretical model calculation, and the list 3 is the efficiency is too low. So that's only the one possibility is the VUV-induced dissolution. However, in the dense cloud, lose the interstellar, the VUV field cannot just penetrate into the core of the dense cloud. It's because the dense cloud, the density is too high, and no matter it's like the dust or the molecule, it will absorb the photon and also scatter the photon. So that means it seems that the VUV, the photon irradiation, is not the root cause for the photodesorption in the dense cloud. However, in the 1989, the graduate, he just do the calculation, and he said that although the interstellar UV field cannot penetrate into the core of the dense cloud, but the cosmic ray can. So, and inside the dense cloud, there are so many hydrogen. So when the cosmic ray interact with the hydrogen, we will just let it ionize or go to the excitation, the state. So when it go back to the ground state, it will emit the induce the secondary UV field. Okay, so, and this is the gradual, the calculation, the result. So here we can see this one is the atomic hydrogen emission, so it's a Lyman alpha. Actually, at a higher energy, still a lot of, but because our system, we only can produce the above like the 114 nanometer. So I only show this the range. And the other is like the Lyman band. This is the molecular hydrogen emission, and also the molecular hydrogen emission in the Werner band. Okay. And in 2000 and 2004 in Leiden University, so Chen et al. And they published one paper say that the cosmic ray induced the secondary UV field is about 10 times more efficiency in depositing the energy in the ice than the direct cosmic ray energy deposit. Okay, so after this, the modeling calculation, the result published. So from that time, so many groups start to do about like the UV irradiation cause the interstellar ice photodistortion they studied. So
is that just because most cosmic rays are absorbed by hydrogen atoms?
Yeah, it's the cosmic ray react with the hydrogen atom or hydrogen molecule first.
But it will be 10 times more, right? So any time a cosmic ray hits the dust grain, you're done, and it goes 100% goes to the dust grain. So
Yeah.
what you're saying is that 10 times more, at least 10 times more,
Yes,
cosmic rays absorbed by just isolated molecular hydrogen.
yes,
And then that emits Lyman Werner or whatever,
yes, yes,
which, and that radiation gets absorbed by the dust.
yes, yes. Yeah, actually, absorbed by the dust or absorbed by the ice molecule. So the cosmic ray, when the cosmic ray reacts with the interstellar ice, because its starving power is too low, so it can very easy to transfer it. So only deposit very few energy. But the UV field, because it's the photon, so the photon we need to consider about its absorption cross-section. So the absorption cross-section I will introduce later. The absorption cross-section is very high, so it can absorb the UV, the photon very efficiently. Okay.
And so let's just understand what's the picture. So a cosmic ray hits a hydrogen molecule typically.
Yes.
And then you generate a very high energy photon.
Yes.
And that scatters and generates many lower energy photons.
No,
Continuum.
it's reacted with the hydrogen atom or molecules, and lose the hydrogen ionize or go to the exciting state, the molecule or the atom. When it's come back to the ground state, it will emit the induce the secondary UV field.
Because cosmic rays, is this like many GeV
Yeah,
cosmic ray?
yeah,
But in a GeV cosmic ray, there's nothing left of the hydrogen atom. I mean, that just completely dissociates, right? You get a high energy electron
yeah,
coming off.
yeah. I know, but actually in the dense cloud, the most the molecule is the hydrogen.
Yeah, exactly. Yes.
Yeah. So if the really to talk about and what is the flux, by this way it's pretty low. It's very low. But even low, but it's deposited the total energy to the ice is 10 times more than compared to the cosmic ray directly to deposit energy. I should actually, because today I did not prepare in this paper. Actually, he do a lot of the calculations, so one by one. So if you interested in, you can check this. Actually, the citation is pretty high. Yeah. Okay. So I keep going, and if we have the time after the talk, maybe we can discuss with this issue. So after that, and I just draw a time map, and we can see from the 2007, the first paper published talk about the photodistortion of the CO ice, and it's like the range is the 10 to the minus 3, the molecules per photon, and then the 2010 is this one is very similar, but another one is almost one order of magnitude higher, and then you see it's the 1 or 2 orders of magnitude higher, and here is the going up and then go down. But I want to special mention that, and list the 3 circle published from the same group, Okay, so and
There's a magnitude difference.
yeah, it's almost 2 orders. Yeah.
It's minus 3, but that's
Yeah.
1.
Yes.
Minus 1.
No, it's minus 1. So
Purple.
yeah, purple. Yeah, it's almost, so it's more than the 100 times. Yeah. So I was quite curious what happened and caused so huge difference from the different groups, and even in the same group they also published so different result. Okay, So, and in this field, usually just as I mentioned, we use like the quartz tube and pump out the air, and then introduce like the hydrogen gas into the quartz tube, and then use the Tesla coil and to provide a very strong field and to just pull out the electron. And then this is the cavity, and connect to the microwave generator. So this is just like the teeny the microwave. So when the electron pull out by the strong the electric field, so it can get energy from the microwave. So it start to produce the plasma here. Okay. So, but as I mentioned, our chamber is an ultra high vacuum chamber. So the pressure is the 10 to minus 10 torr, and the inside is the quartz tube. The pressure is like the sub torr. So the pressure difference is too huge. So we need to put a window to separate the two systems. So usually we use the magnesium flat window. Okay, so compared to the grade of the calculation, and the red one is the UV lamp, the emission spectrum. So you can see because it's a hydrogen atom and the hydrogen molecular emission, so it's quite a match. Okay, and then I want to find out is due to some reason and because the different group they publish the different photodesorption yield. So the first one, I think maybe is due to the operation configuration of the UV lamp quite different. So I try to change the hydrogen, the pressure. It's from the 0.4 torr, 1 torr, and the 10 torr. Actually, when I put more than the 20 torr, I cannot discharge the hydrogen. And when the pressure is too less, the plasma is very unstable. So you can see when the pressure of the hydrogen become higher, it's reduced the lambda alpha, but it's increased the molecular emission. I think it's quite makes sense because in this case, when the hydrogen atom the number density is higher, and the hydrogen atom emit the lambda alpha, it will absorb by another one, so it cannot go out. Okay, so and they are the two type the geometry. This one we call is the T type, and this one is the F type. And this is the most, like more than the 90% the laboratory, they bought the UV lamp from this company. But here I will not say this company the name because this company they try to sue me because I just reported there the lamp is not very good. Okay, in the international conference. Yeah, but it's occupied the more than the 90%. Okay, so I want to mention that if I bought it, it's the $700 USD, but this is only a 700 New Taiwan dollars. Okay. So we decide this and find a local the company to produce the quartz tube for us.
So the difference is one is a Taiwanese company, the other one is not.
This one is we design and find a local the company to produce it for us. Okay. Okay. So it's quite cheap. So before we start to produce the quartz tube by ourselves, if every time when the student I cannot say they are not so carefully. They still very carefully, but still just broke it. So they will feel very guilty and very uncomfortable and to knock my door and say, blah, 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 beautiful, blah. But now they just like broke. Okay, change another one. Yes. Okay. So let's see. So this is a geometry effect. So even with the same pressure, but we change the geometry, you can see in this F type, it's also reduced the lambda alpha. Actually, it's also very easy to understand it because we cannot measure the pressure of the plasma. So we measure the pressure of the hydrogen gas before we let it inlet into the quartz tube. So the pressure is the same, but you with the one corner, so you will reduce the pumping speed of the pump. So it makes the density is higher. So as that's the slide says, when the hydrogen, the atom, the density is higher, it will absorb another the hydrogen molecule emitted the lambda alpha, and another is in the ground state, it will absorb this energy, go to the excited state. Okay. So, and we also try to produce the high purity, the lambda alpha. So we just use the gas mixture and with the helium. So helium will just isolate isolate the hydrogen atom. So this hydrogen atom will not interact with another hydrogen atom. So you can see it's the quite pure and reduce the hydrogen molecular emission. So in this case, the percentage of the Lyman alpha is almost the 80%. Actually, with the argon, it can go to the 99%, but it will reduce the photon flux very too much. So we cannot use with the argon. And we also try with the different window material. And usually we use the mesophyte window. So here you can see because the cut of the wavelength of the MGF2 is like the 114 nanometer. So we can still have the Lyman alpha. But calcified window is a cut off the wavelength is the 123 nanometer. So it will cut off the Lyman alpha. So by this way, we can compare with the Lyman alpha and without the Lyman alpha the effect. And we also consider about because the window material, if you bought it from the different the company, maybe it's transparent. For the Lyman alpha, it's totally different. Okay, so the A grade is from the Russia company, but unfortunately, and we cannot buy the material from the Russia company 2 years ago because it's due to the war, and the Taiwan bank cannot transfer the money to this company. And the B grade is from the UK. And the price of the B grade is 10 times more than the A grade, 10 times more. So when I found the Russia company and my senior classmate, and now he is working in the single stream radiation center, and he just warned me, oh, maybe the quality is very bad, so I merge it. And the A grade is 10 times cheaper, so it's a Lyman alpha the transmitters and can reach the 70%. And this one, the B grade is much expensive. It's only the 10% can transparent. So sometimes it's not the goods. It's more expensive. It's the performance is better. Sometimes it's not. Okay. So how do we measure the photodistortion E of ice? So here I introduced this infrared spectrum of the CO, this molecule in solid phase. Okay. So the temperature is roughly close to the 10 Kelvin. So CO only have the one absorption feature in the middle infrared range, and it's located around the 2140 Wm number. So you will see it's a double peak. So this is the transverse mode, and this is the longitudinal mode. Okay. So and here we define that the 1 mole. The 1 mole means like the 10 to the 15 molecules per centimeter square. So when the current density reach to the 10 to the 15, we call it 1 mole. So it's almost can just cover like the surface. Okay, so we start to use the UV to irradiate this ice. So with the irradiation, you will see its absorption, the intensity decrease. That means the less and less the CO, the molecule still on the substrate. Okay. And so when we just run out the window, and we see this is the before irradiation, so here is only a CO, but with the irradiation, then we can find the CO2 produced. Okay. So,
sorry,
yeah.
I'm very unfamiliar with this. Is that 5 micron? I just don't know what a wave number is. It's 5 microns if you
no, this is
centimeters.
Yeah, this is
I just don't know wave numbers. I just know micron and wavelength.
Okay.
That's 5 and
so let me transfer it. So it's just a 1 divided by the Wm number is become the.
But do it for me, please. It's 5 microns.
I remember. So let me think about. So the 4,000 is like a 2.5 micrometer. 4,000 Wm number is about
4 microns. Right?
Yeah.
And that's the vibrational line.
Excuse me?
It's vibrational CO.
Yes.
Mm-hmm.
Yes.
No. Yes.
Yes.
Thank you.
And this is the vibration of the CO2. Actually, CO2 has because CO2 has the 3 atoms, so it has more. This is the stretching mode, and the bending mode is around like the 900 Wm number. It's very close to like the 20 micrometer. Okay. So and according to the carbon balance, so we can know that. So when the CO deplete, and it will contribute to form the CO2. So the S means the solid phase. And when this the two, and it's a chemical reaction, but it also can do the desorption. So it's maybe dissolving, and the CO in gas phase, also the CO2 dissolving in gas phase. Okay. But however, because the dissociation energy of the CO is the 11.09 electron volt, and via this the dissociation the process. But the MgF2 is cutoff energy is about like the 10.9 electron volt, so it's lower than the dissociation energy. So that means all the UV lamp cannot dissociate the CO molecule directly. So how is the to produce CO2 is via the like the exciting state react with the ground state and to produce the CO2 and kick out the one carbon. Okay, so by this way, that means the one CO2 formation needed to the CO molecule to deplete. So that's why here we put a factor of 2 here. Okay. And this is the quadruple mass spectrum. We can see that during the irradiation, we can see that some of the signal is increased, and that means that like the mass 28 is means the CO, and the mass 44 is the CO2. And here I use the it's not so clear. You can see very light the background, and this is we turn on the UV lamp. So we turn on, the signal is increased. When we close, it's the decrease. So that means that this distortion is caused by the photon irradiation. Okay, so so how can we calculate like the dissolving the total molecules? So this is a typically the CO, so it will format the CO2 and cause the CO dissolving and also CO2 dissolving. So by this way, we just need to do the depletion of the CO and subtract the 2 times of the formation of CO2. The others is the contributed to the distortion. And if we check the mass spectrum, you can see the CO2, the dissolving, the signal is very, very weak. So we assume the most, like more than the 90% is contributed to the CO dissolution. So by fitting this the data point from the infrared spectrum, and the slope is equal the photo distortion yield. The yield is means you insert one photon and how many the CO molecule can dissolve out of the ice surface. Okay, so and our result shows that this number is for the Lyman alpha proportion. So you can see the Lyman alpha the proportion around like the 20% is get higher the photo distortion yield, and with the very high the proportion of Lyman alpha is the lowest, and the others is in this range. So the difference is like the factor of the 5 to the 6, but only the 5 to the 6. So how is possible we have in this field we have the 2 orders of magnitude difference? So I thought I did not just approve it yet, because most laboratory they bought the photodiode, and this photodiode is from the same company. There are 2 types, but no matter which types, you can see the range is pretty high from the X-ray, the soft X-ray, then to the EUV, to the vacuum ultraviolet, and to the ultraviolet, and to the visible, and to the infrared. So, and I just quickly switch back to the lamp. Oh, sorry. You see, when we light is on, and what you can see, it's like a pink in color. So that means is the visible photon still very high. Okay, so in this way, if you just put a photodiode directly to the UV lamp, it means that you not only merge like the UV photons, but you also merge the visible the photon and even the infrared photons, and that will cause the photon flux too high. So when the photon flux is too high, and that will cause what happens? It will reduce the photo distortion yield. But in our study, we do this the 4 different configuration the experiment in the same system with the same lamp, and we use the nickel mesh to do the in situ measurement of the photon flux. So why in the same system we still have this the difference? Okay, so now before we talk about this, the first step we need to think about is when we talk about the photo distortion, the first important step is the photon need to be absorbed by molecule. Okay, so we want to know if this molecule like to absorb which kind of wavelength the photon. So we set up the system, and in this system you can see it's just like the normal system, and there is UV lamp, and this is substrate, and behind this the UV chamber we just equip it with another monochromator. So before we deposition the ice, we measure the UV spectrum of the UV lamp first. Then we start to deposit ice like a CO, and rotate it 90 degrees, use the infrared to measure its current density, so we can know how many the CO molecules on the substrate. And then we switch back and do the measurement again, so this becomes I prime. So according to the Beer's law, we can get is the absorption, the cross-section. So here I show you that the CO, the red line is CO at the 300 Kelvin, so in gas phase, and the CO at the 15 Kelvin is in solid phase. So you can see it's a huge difference. So even is the threshold, is also the different, like the, I would say like the 5 nanometer different. So it's a huge difference. I try to find like the physicists, and they are doing about like the atomic, the electron structure calculation or molecular structure calculation, but they told me it's too difficult. It's too difficult because I'm not talking about the one molecules. It's a lot of molecules, so it's impossible to solve this issue. Okay, so I don't know why it's the shift, and but it's become broad. It's quite easy to know. It's like a collision broadly. So when it's in the gas, the density is very, very low. So the molecule collided with another molecule, the possibility is very, very few. But in the solid phase, it has a lot of the possibility. The A, the CO molecule, is the electron cloud will affecting another one. So it's caused this broadly.
So what's going on? So at 15 Kelvin, the CO is solid.
Yes, solid.
And at 300, it's gaseous.
Yes, gaseous.
At what density?
The density is very low because when it's too strong, too high, and the VU photon cannot penetrate for the whole cell, so it's very low. For this one, it's like the 10 to, I would say like the 10 to 8, 10 to 8, 10 to 9 per centimeter cubic.
And then the blue line is at 10 to the 20?
It's like the 10 to the 16. 16, yeah, 16. Because we deposit like the 10 molar layer. 1 molar layer is the 10 to 15 per centimeter squared. So if the 10 molar layer is become the 10 to the 16.
How did you calculate?
The layer is from the infrared. It's also according to the Beer's law. So because the absorption strength is just built up in the database. So according to the database and with the Beer's law, we can know from the absorption, we can know is the current density.
So what's the link? The link is from there to that.
Excuse me?
The link for your calculation.
Oh, you mean the link?
The link.
Oh, the length. Okay, the length. Actually, the current density equals the length, the thickness. Because the current density is the density times the optical path. So optical path is like a thickness. So we assume that the density, the number density is very uniform. So when the infrared passes through the eyes, and we can calculate what is the total current density. So we will know it's the optical path. So we just assume it's the optical path equal to the eye thickness. Let me try this one. No, not this one. Wait a minute. Yeah, like from this equation. So this is the original intensity, and this is the penetrated intensity, and this is the exposure to the. This is the number density, and this capital L is the optical path, and this is absorption cross-section. So if we know the absorption cross-section and also know the I0 and I prime, so we will know it's the optical length, it's how much. Okay. So I just show the absorption cross-section in the UV region of the CO, and with the emission spectrum of the UV lamp, you can see. So before I published this paper in 2014, and before that, so many the papers talk about irradiation always say that Lyman alpha irradiation of COIs. our Lyman alpha induced the distortion of COS. But we can see CO didn't like the Lyman alpha. So the absorption almost like a 0. So that means the CO will not absorb the Lyman alpha photon. But this guy, you can see is the resonance state is here. It's located in the hydrogen molecule emission. So that means the CO like to absorb the hydrogen molecule emission, but didn't like to absorb the Lyman alpha. But however, it will produce in the COIs, the product is a CO2. So we also merge the CO2. Okay, so but you can see the CO2 absorbed in the Lyman alpha region is higher than the molecule emission. So it's totally different. So that means when we just do experiment in laboratory, and we need to consider about not only the parent molecule, but also the products. We also need to think about it.
Just to see, I'm not sure I follow exactly why your solid CO ice has pressure broadening, since your actual pressure is 0, right? So it's just the van der Waals forces that are coupling one CO to the next one in the ice.
Yeah.
But this is electronic condition, right? So you got an electronic condition, and your van der Waals force is enough to broaden this by a few %.
Yeah. Actually, if you compare to the gas phase, you will see its broadening is super huge. That is because, yeah, you are right. But in the solid phase, because the CO and with another CO, their distance is very short. Like the Armstrong, in Armstrong the range. So that means the molecule is the electron cloud will affecting another one. So
I mean, it's van der Waals only. It's only in ice.
No, not only the van der Waals force, but yeah, but if you say the van der Waals force is also okay, because it's we call it a dipole-dipole interaction. So the dipole-dipole interaction is also considered about like I will not talk about today. So at a different temperature, when it's the CO landing on the substrate to form the ice, sometimes it's the neighbors is only the 1, sometimes it's the 2, sometimes it's the 4. The maximum is the 8. So this is according to the collaborator, they do the Monte Carlo simulation and tell us. So that means the different neighbors. That means it's coding the binding energy is totally different. That means the one CO molecule is affecting by the only 1 over to the 8. This is random. So it will cause the huge broadening. But still, I cannot answer the question very precise. Is because I try to find the collaborator to do the electronic state calculation, but they always reject my proposal. Yeah, but they say only the one molecule is so complicated. How can I merge so 10 to the 15? What are you talking about? Do you know? Always like that. Okay. Okay, so here and I change back to the figures. But here I want to just mention you here. You can see actually the depletion of the CO and the substrate to the formation of the CO2 is quite linear, and till the iciness is the thickness less than the 5 molar. So you can see it's the photodistortion efficiency become less and less. And why less and less? So we propose that in this field, and this is proposed by the Leiden University, and they said that the photon absorbed by the inner ice, the molecule, because the inner molecule, when it's absorbed energy, there are only the 2 ways they can do. One is absorb energy and do the dissociation, chemical reaction. Otherwise, it's just go to the excited state, then release the energy. So when the inside, so when the inner molecule release the energy, it will transfer propagation to the surface layer. Actually, it's true everywhere, but we're also to the surface layer. And when this the surface of the molecule accumulated enough energy, so that is the desorption. So it's called the desorption induced by electronic transition. We call it DIET. Okay, so this is proposed many years, but no one to just prove that. Okay, so according to the result, so we think about that. So when the UV photon passing through the whole ice and the energy absorbed by the layer 2, layer 3, layer 4, they will contribute the portion, the energy to the top layer. And the top layer, the longest transfer energy, the length is the 5 molar layer. That's why, in this case, you will see when the icing is less than the 5 molar layer, then it becomes decreased. It's because the energy, in this case, is from the 2, 3, 4, 5. And the next one is also from the 2, 3, 4, 5. But when the I thickness is less than the 5 molar layer, that means it's like the energy from the forbidden layer to here. So the accumulated energy becomes less, so it starts to decrease. We propose that we did not, we don't have any calculation or the experiment can prove this. Okay, so and now in this field, the group they accepted what we talked about. So we think that the energy transference is a 5 molar, but what is the mechanism behind it? How is it transferred? So and the first proposed by the most group is like the forced resonant energy transfer. That means the donor and the acceptor, they need to have the electron state overlapping, otherwise the energy cannot be transferred. So how to prove this? So we find two very good candidates. The first one is a CO and another one is N2. Here I mentioned that you can see here the N2 is the 5,000 molar. That means it's the absorption cross-section in UV range is very, very weak. So we need to increase the optical length. Otherwise, we cannot observe is the absorption, the spectrum. Okay, so we can see in this region, in this like the 150 to the 165 in this region, there is no overlapping the electron state between the CO and the N2. Okay, so we say we have to do this experiment. So we propose that we deposit the 13 CO isotope CO on the bottom layer and deposit the nitrogen molecule, the ice, on the top layer. Here, why we need to use like the isotope is because if we use the normal CO, the mass is also the 28. Actually, if we bought a very high accuracy, high precision, the mass spectrometer, we can distinguish it's like the 28.0070 something, and this will 28.00 like the 15 something. So we can see it's different, but it's too expensive. So the best, the cheaper way is to use the isotope. Okay, so we move to the synchrotron radiation center, and why we need to go there, as what I said. Actually, this is the red line is the UV lamp we use in the laboratory. So why we cannot use the monochromatic light to do irradiation? You will see it's too weak. So usually we use the broadband to do irradiation, but in the synchrotron radiation, you can see it's a 1, 2, almost the 2 to the 3 orders of magnitude higher the photon flux. Okay, so we set up the one system layer, and we call it the wavelength dependent desorption and the chemical reaction system. Okay, so by this way, and we do the scanning with the different photon energy. As you can see, here we can observe like when the top layer of the N2 ice is a 2 molar layer, and the bottom, the 13 CO ice is a 30 molar layer. So we can see clearly when the nitrogen atom dissolving, but here it cannot absorb any of the photon. So that means the photon need to absorb by the bottom layer, the 13 CO, then transfer the energy to the top layer. But my student told me, but do you see that? We also can observe the 13 CO, the desorption. So that means on the top, the 2 molar layer is not really fully cover the bottom layer, the surface. So it's still the bottom layer, the 13 CO, absorb the energy when it's do the desorption, and the co-dissolved with the nitrogen molecule. I said, that's fine. So we deposit the more thick the nitrogen ice. So in this case, you can see it's a 4 molar layer, and we only observe the N2 desorption signal, and without any the 13 CO. So what does it mean? It means that this kind of energy transfer doesn't need to violate the forced resonance energy transfer. So that means the donor and the acceptor, their electronic state don't need the overlapping, so still can cause this. But when I talked to my collaborator, and he just mentioned me, he just reminded me that, okay, the result shows that clear, but you cannot say in the COIs, pure COIs, they didn't follow the forced resonance, the energy transfer, and we didn't now we are still going on for the experiment for talk about the efficiency between the resonant, the forced resonant energy transfer and the non-forced resonant transfer. What is the difference? Okay, so here just the summary quickly. So when we talk about the photodesorption of the interstellar ice, and then we need to consider about is the molecular, the absorption cross-section in solid phase. Otherwise, we can know what happened. Okay, the second is the photodesorption of interstellar ice involves the contribution of energy from the multiple bottom layers to the surface layer, and then making the mechanism at the distance of the energy transfer an important topic of the study. So here, this topic is still quite popular. And the last one is the what I said of the previous slide. Although we just demonstrate that between the CO and the N2 ice layer, the energy transfer don't need the electronic state overlapping, but we didn't know which kind with the overlapping electronic state or without the overlapping electronic state, which is more efficiency. So now we still need further experiment to prove it. And here I want to thanks to the field student and Dr. Huang, and he got the PhD like 4 years ago, and now he's the research scientist in the synchrotron radiation center. And this is my master student, and now he is working in the Academia Sinica in the Department of Physics, and working for the Chen and for like the quantum computing the component. And this is my recent graduated PhD student, and Dr. Xie, and she is the postdoctor in the Hokkaido University. And I cooperated with many friends, and in the NASA Amsterdam Research Center with the Michel Nuevo. I think maybe the Chen know him very well. And I know this guy when I was a PhD student, and he was postdoc. So we cooperated till now. And the topic we cooperate is like the amino acid formation, sugar formation, and also like the purine formation. So it's the complex organic molecules. And in the Italy group, and I cooperated with Dr. Travera and Professor Cecchi Personini and Dr. Jimenez Escobar for X-ray, the irradiation study. And in Germany, and I cooperated with the Professor Conny Jäger. Conny Jäger can produce like the dust, like the carbonaceous dust or silicated dust. So, and recently we studied about like the dust effect of the interstellar ice is cooperated with the Conny Jäger. And in Spain, and we cooperated with Dr. Maiza Carlo and this guy, and bring me into the photodesorption of the CO. So, and from the first day to now is more than like I would say the 12 years. Okay. So, but we still don't know the CO guy very well. And in the Holland, and we cooperate with the Professor Castro and also Professor Yu-Jung. Yu-Jung was my PhD student, but actually I cannot say he was my master student, is because in that age I was the postdoc only. So I would say he is my junior classmate, and now he got the faculty position in the Leiden University. Okay, so do I still have time?
You have 5 more minutes.
Oh, 5 more minutes? Okay, 5 more minutes. So I want to show you quickly. Okay, so usually we talk about interstellar ice. It's condensed on the dust grain. But in the lab, what kind of material we use for the dust grain? It's a window. It's a very smooth window. Okay, so the traditional models talk about it's like the thick multi-layers. So ignore the monolayer. We call the monolayer is the ice molecule contacting with the dust the surface. That's called the monolayer. Okay, and this model also assume that the homogeneous surface. So ignore the chemical heterogeneity. So that means it's assumed that every site they are so uniform, no any difference, and also the intermolecular force. So it's ignore the molecular dust interaction. Okay, so I quickly just jump to this way, and so I cooperated with the Conny Jäger, And Coney used the laser aberration. So when the laser hit the target, the 13 carbon, it's like the disk. And it will just the shockwave formation, and so it's produced the plume of the 13 dust. And then we use the helium and just flow loose the dust, and passing through a skimmer and to condense on the surface of the calcified window. So this is the actually, because we use when we produce it, and we use like the vacuum bag and to suck out the air, because we don't want to just have the contamination. So under the field emission, the scanning electron microscope, you can see it's just like a sponge. It's around the pores. Okay, so I want to show you is this. This is the CO deposit on the window, smooth surface. You see clear double peak. But in the carbonaceous, the dust, you see it's quite broad. It's totally different. It's totally different. So I skip the more. Here is the CO2. You can see CO2. And this one, the S-band, when the S-band you can see is clear, and without this another bands, it means it's the very pure the amorphous, the CO2 ice. But when it's the star, like the partial the amorphous CO2 ice and partial crystalline CO2 ice, it becomes like you can see the TO mode and the longitudinal mode. But compared on the dust surface, you never see this the two peak. It's broad. We try more than the 20 dust sample and more than the 100 experiments. We every time see the same result. Recently, we will try to publish it. But with the water, you see, almost different, almost the same, no difference. So here, because of the time problem, so I will stop here. I will just want to let you know. So now the JWST just reported mainly the infrared spectrum, and usually compared to the laboratory data, we always use this kind of CO2, this kind of CO, not like this kind. So we need to think about it. The result of the JWST tell us it's really from the CO2 or something, or is with another one. Okay. So thank you for your attention.
Do you want the summary? Do you have a summary for the second talk?
Yeah.
Maybe you want to go all the way to your summary.
Okay.
What's the summary?
The summary is we cannot ignore the dust effect for the real in the space, the absorption spectrum. Yeah. So if we still use like the laboratory spectrum, maybe we will get in trouble. It's not the real deconvolution. It's the fake deconvolution. Okay.
Thank you.
Thank you.
So, questions?
Thank you. First of all, just clarify that I don't work on any of this, and I am totally ignorant. I'm probably the most ignorant in this whole room. Keep that in mind, okay? So I'm asking the most basic questions.
Okay.
I'm probably the only person in here who's never worked on the ISM, so I'm far removed from knowing anything about anything. So it's very naive. Sorry to ask simple questions.
Okay.
But yeah, so you mentioned that one of the motivating reasons is the existence of, say, CO and other free molecules in the molecular clouds. Yeah. That whose mechanism, it sounds like, is not understood of what the energy, the cosmic rays and how those cosmic rays keep those things floating around instead of sticking to dust grains, I think is what's being asked. So for this question, do we now know the answer because of lab work, or is it still ongoing, or what is it going to be? Actually, now we can say that no matter with the electron irradiation or with the proton irradiation, just the energy source, even the hydrogenation, it can cause the molecule dissolving out of the ice surface. But it's due to like the efficiency problem. So now, and someone will say, you see, the UV is the most efficient candidate. But recently, in the Hokkaido University, in France, they published many papers talk about the infrared induced desorption. But they use the free electron infrared laser, and the flux is pretty high. Although they just claim that each of the molecule only absorb like the 0.2 the photons. But I told them, but
how can you just know that your intensity, the population is very uniform? So sometimes maybe some part is more than the one. So that's we call it the multi-photon desorption. So multi-photon desorption will not happen in the dense cloud, because in the dense cloud, what they claim is because in the dense cloud, infrared photon flux is higher than the UV photon. I agree that, but I never think about the infrared photon can cause the photodesorption. But so there are so many different the energy sources. Always can see the photo-induced the molecular desorption. But now the problem is which one is more efficiency. But this is the only which one is more efficiency. But the problem is what is the mechanism. So in the Leiden, the Ventishark, and she proposed that is the kick out. But the kick out is from the water, because the kick out is when the water absorbs energy, it's dissociated, become the OH radical and the H. And the OH radical will just colliding with another molecule, and cause the chemical reaction or directly the kick out. So, but there are still a lot more than 10 different models, but we don't know which one is the more suitable for the real case. So we are still going on to figure out what happened. But I have to say, this kind of experiment need very, very carefully and much time. So the 90% of my students, they don't like this topic. But I always want to convince them to do this, but they say no. And 2 years ago, and I convinced one guy is the master student, and so I have 2 proposals for you, and one is the 5-star. It means it's very difficult, and I don't know what happened. So maybe 2 years later you cannot graduate. And another one is the 3-star, and I already know I can just guess, and it's the result. So which one you want to choose? And when he want to choose this one, okay, so then he chooses this one. So that's why. And I can show you the data here. I quickly go back. Yeah, this one.
This is
and
three-star.
Yeah. So this is the master student did it. And so the first year, I just asked him, go to a synchrotron, start to set up the system. And I just say, oh, okay, bye. So see you one year later. And the second year, and he spent a lot of time to do this one. Actually, each spectrum need to spend 7 hours because it's a scanning. And the signal is quite weak. So the mass spectrum we bought is the counting mode. So for the photon energy, the single photon energy, we need to count in the 3 minutes. So it's the 0.1 nanometer each step. So why the step? So he need to spend many hours to do it. So I think I hope I can answer your question in next 10 years.
Okay, that's a very good progress.
Okay.
I'm not working on ISM either, so a naive question. Does photodesorption occur at higher temperatures as well?
Yes.
So, for example, on Earth, let's say we don't have oxygen, we don't have ozone, and UV can penetrate. Can that affect the water cloud, ice clouds?
Yeah, but usually we talk about is okay, I didn't mention it. So when the parent molecule it cannot easily dissociate by the UV photon. It will dissociate by the whole molecule, like the CO. Because the CO, the dissociation energy is 11.1 electron volt. But our photon, the highest the energy is only 10.9 electron volt. So it cannot dissociate. So that means that this kind of the molecule absorb the energy. It will not dissociate, but it can violate the dipole-dipole interaction to form the new product. But the most possibility is the whole the molecule do the dissociation. But for example, like the methanol is quite easy to be dissociated by the photon energy more than the 5 eV. So that means that it will dissociate and become like the CH3, or is a CH4 produces CH4, then cause the CH4 dissociation. But this dissociation is not from the CH4 molecule directly. It's from the methanol dissociated to form the methane, then do the dissociation. So your question is, I would say yes, because the UV photon can just react our atmosphere, the molecules, and the course is to do like the chemical reaction and produce the newer product, and that is the product to do the desorption. I'm not so sure if I understand.
So
Yeah.
it depends on dissociation.
Yes. Yes.
Dissociation.
Yeah.
Yeah, thanks.
Yeah. You're welcome.
Any more questions?
So I have a question and a comment together. So
Yeah.
question is, do you now, for the second part of your talk,
Yeah.
do you now have a new library of the CO, water, ice absorption, and the near-infrared with dust effects?
The dust effect, no, I don't know this. So there is already the library. Also, it's the.
I guess you show new results that the two peaks are blended together with the dust effects.
Okay.
So you have the slide. Right?
Yeah.
You have the slide with two peaks. One down the left, there are two peaks, but down the right,
Yeah.
there's the dust. That's only one peak.
So that is at least one new template for CO, I guess, CO2.
Okay.
And the reason that I'm asking is because so I'm part of a new mission called Saphirix, which just started and will observe about 10 million
Okay.
near-infrared spectra.
Yeah.
And 10 million is the number of spectra that we expect
Okay.
significant AV, at least to have some detectable absorptions. And then, so I'm not an expert on this subject, but I think they are going to have a few different ways to interpret the spectra. The first few ways will be more empirical, like just measuring the equivalent width. And then I think till the end, the more involved way is to compare with this kind of template.
Yeah.
And then, well, I can only guess that they might be still using the double peak ones if they are. Those
Yeah.
are
Yeah.
things on the market.
Yeah. I think just like what you said, normally they will use like the library and to do the deconvolution. But now we show it's not a double peak, so it's only the one propane.
Yeah.
Yeah, I know actually not only our group start to dealing with this the dust effect, but also the many groups in the European, especially in Leiden, they also did this kind. Yeah. But so far, I didn't see any of the group publish this kind of paper yet.
Is yours out already?
Yes, not yet. It's still ongoing. I push my master student need to finish the first the version quickly.
Okay.
Yeah.
We'll chat with you after.
Okay.
Okay, any more questions? So let's thank Yu-Jung.
Okay. Thank you.